So now that we've looked at some of our energy, we need to talk about and work. We need to talk about potential energy. In particular, this one's going to be about gravitational potential. Okay? If you remember the definition of work, excuse me, work is force dot displacement. Okay? So when we're dealing with potential energies, we're dealing with some of the classical forces of the universe. We're talking about friction, we're talking about gravity, we're talking about springs, we're talking about even tension for that matter. All those forces are what we're talking about when we're talking about force. And all of those can accomplish work. Now, gravitation and spring, if you look at the equations or you look at the fundamental concepts when you're talking about gravitation and spring energy, it's all kind of positionally based forces. I get gravitational energy, even electrostatics for that matter. I get gravitational energy, I get gravitational force if I'm in a position inside a gravitational well. If there's other objects there and those other objects are in a position nearby. Same thing with springs. I experience the force of a spring by simply compressing or expanding that spring. So they're positional based energy. And by definition, that's what potential energy is. All it is positional based energy. Now, mechanical energy, when we talk about potential energy, we're really only talking about two sources of potential energy. We're talking about gravitational potential and we're talking about spring potential. Now, there are other forces of potential energy. Electrostatics is a perfect example of that. Even magnetostatics, you can develop some sorts of energy. An inductor is a perfect example of that. But mechanical potential energy, we're talking two. We're talking gravitational, we're talking spring. So the one we want to talk about now is we're going to talk about gravitational potential. Now, we're going to talk about using the example of force being weight instead of Newton's laws on potential or on universal gravity. And the reason for that is that when you start talking about gravitational energy, when you're talking about the universal gravity, there's a couple more terms that we have to come up with before moving on. Okay? So this is just simple mechanical, the idea of weight being a force. Okay? So the force is weight. Okay? Cool? So F equals mg. Now let me darken that equal sign a little there. Okay, F equals mg. Now the direction of the force of gravity we say is always down. It's actually always towards the center of the Earth, but we pretend that the world is relatively flat. And for the most part, most people on the planet believe that it is flat. It's one of those things that, common knowledge is a load of crap because it looks flat. Okay, so we're going to say the force of gravity is down. Okay? So now if we're talking about displacement, we're talking about displacement in the direction of this force vector. We're talking about displacement either this way or this way. Okay? So we're either talking in this direction or that direction. So that displacement we can call by something else. We can call it by a change in height. Okay? And it's really important to say that it's the change in height instead of simply height. Because I live in Colorado. My height is over a mile high. Okay? But it's my change in height that determines my potential energy. It's here's my height now. I can climb on top of this cabinet here, and it's the change in height that determines the amount of potential energy I have. Now, if I had a wrecking crew to come through and dig a hole a mile deep, then we could talk about a difference of change in height there, where we're talking sea level to a mile high. But for most cases, we're only concerned about how much the height changes, which is great because potential energy is sort of arbitrary. You can set it one point to be zero wherever you want that point to be. Do I want it to be at zero? Do I want it to be a mile high? Do I want it to be at sea level? Do I want it to be, 6 miles above the surface of the Earth. It doesn't really matter, okay? Because it's the change in height that matters, not simply height. So that means that the equation for energy, gravitational potential energy, which potential energy is normally expressed as a U, okay? It's also expressed as a PE, depending on what text you're looking at. And then to denote that it's gravitational, we tend to add just a little g next to it. Well, those equations are m, little Hewitt moment there, drew an extra m, is going to be the mass of the object times the acceleration due to gravity, weight, times the change in height. Okay? So that means that the gravitational potential energy is going to be mgh. Now, I can gain gravitational potential energy if my change in height is positive, if I go up, or I can lose gravitational potential energy if my height goes negative, I go down. Okay? The really interesting thing is when you talk about work, though. I have to do, gravity does negative work as I'm going up. Think about it. It's slowing the object down. And then gravity is doing positive work as it's going down. It's speeding it up. It's changing the state of that object. Okay? So, gravitational potential energy, mg delta h. It's the change in height that matters, not the height. The change in height that determines its gravitational potential energy.